Heat holds the young planet in a slow red glow, a world wrapped in incandescent rock where the surface moves like heavy syrup, and the horizon quivers with rising haze. The early Earth, newly assembled from energetic collisions, radiates its stored heat to space. The global magma ocean cools by radiation, and by the slow overturn of convecting melt and crystals begin to form and migrate according to their densities. Ultramafic minerals like olivine and pyroxene grow first, some sinking to deepen the mantle, others accumulating in transient roughs that thicken the uppermost skin until a fragile lid appears. It is a real process measured today in laboratory phases, high-temperature experiments, and the chemistry of archaic minerals. The planet differentiates even as it breathes heat, and a first crust mostly basaltic spreads in dark, thin plates across incandescent seas. The lid does not last. Impacts pummel it, plumes pierce it, and the thin rock founders back into melt yet in each pause. Between ruptures the surface thickens again like the quiet skin on a cooling soup bowl, and each interval leaves behind a little more solid memory. Inclusions inside the oldest known terrestrial minerals, tiny zircons later carried into younger sandstones of the Jack Hills, keep a record of these beginnings, their hafnium and oxygen whisper, that crust separates from mantle, early within the first few 100 million years, and that liquid water likely touches rock by about 4.3 to 4.4 billion years ago. Only a few durable crystals smaller than a pinhead survive the eruption and burial of whole provinces, a dry observation the size of a breath. Only a thin rind, mere tens of kilometers against a planet, thousands of kilometers deep, emerges from an ocean of fire, a mild irony written in basalt and glass. Only by shattering and reforming over and over does the surface learn how to persist, another soft paradox of endurance taught by destruction. The air above the glow is thick with exhaled volatiles opaque to the weak early sun, and clouds across the future sky condense and evaporate in pulses. But rain remains more omen than presence here, and water waits its fuller moment. Cometietic lavas hotter and more fluid than almost anything modern volcanoes deliver stream from fissures, their cooling surfaces roping and folding. They testify to higher mantle temperatures and to a world where heat moves fast but continents move hardly at all. Whether a global plate system already stirs beneath this lid is uncertain. Some models favour a stagnant cap episodically broken by plumes and impacts. Others imagine short, fast cycles of subduction and resurfacing, but the record is patchy, and much of it is gone recycled into the deep. Yet the physics remains simple in its patience as heat escapes, viscosity rises. As viscosity rises, convection slows. As convection slows, the lid thickens, and in that thickening local buoyant melts richer in silica. Gather, rise and stall, foreshadowing the granites that will later anchor continents. Zircon titanium thermometry hints that parts of the surface cool to temperate conditions early. If so, hydrothermal systems already etch pathways into basalt, leaching elements and creating clays that prefigure sediments. Radiogenic isotopes in uranium, thorium and potassium keep the interior warm, slowing the planet's exhale. Latent heat of crystallization releases energy as melts, freeze retarding the drop in temperature. The surface answers with brittle fractures that let new lavas out, and with each eruption the atmosphere receives more volatiles, thickening the cloak that slows the night. The first crust is mostly basalt and komatiite, denser than the granitic rocks that will come, so it rides low and drowns easily. But where buoyant residues accumulate perhaps along plume heads or impact rarefied chimneys, proto-continental materials begin to separate silica-rich water-bearing light enough to linger. Here a lesser-known detail waits in the quiet minute mineral inclusions inside Hadean zircons, quartz, muscovite, even possible apatite suggest that the magmas interacting with these grains, once cooled in settings, not unlike continental crust, a hint that continental-style processes flicker in and out, long before true continents stand. If these processes repeat often enough, patches of more evolved crust could persist between cataclysms acting as seeds that later cratons will remember. The planet lets the chemistry of hafnium isotopes keep time where depleted mantle signatures tell of early extraction of crustal material, and where remelting adjusts the tune. Heads of rising plumes spread like slow umbrellas beneath the cooling lid, thinning it until tears open and flood basalts pour across old flows, one black sheet cooling against another in gleaming stacks. Whether there is already a hint of plate boundaries, a rift here, a proto-subduction, there remains a quiet question folded in the mantle's memory, but the inevitability of density contrast and gravity's long arithmetic favour cycles of foundering and renewal. Even if plates do not yet travel far, the habit of sinking dense lithosphere is rehearsed in miniature. Each time thickened basalt hydrated and cooled, becomes negatively buoyant and slides back into warmer depths. The scene steadies, a thin crust. Forms is broken, is swallowed and forms again while the mantle below continues to stir with decreasing vigour, and the net effect is progress towards stability without any single moment of completion. By degrees the brightness dims. The brittle lid lasts longer between impacts and plumes, until the planet can hold its heat beneath a shell robust enough to be called surface. Facts persist in this hush. Basaltic crust crystallizes from a cooling magma ocean. Density stratification sorts minerals. Early zircons capture evidence of crust-water interaction. A single gentle analogy suffices. The planet's first crust is the film on cooling broth, fragile, reforming, destined to be stirred yet thicker each time. The mystery remains as it should open and patient. When does plate tectonics truly begin under this red sky, or much later under a bluer one, and how many generations of short-lived skins are needed before one endures long enough to invite rivers and soils? For now the world breathes heat and waits, and in the waiting stone learns to hold together. Steam thickens above the young crust, a pale shroud drifting in currents shaped by volcanic heat and the slow turning of the planet. The air is dense, heavy with carbon dioxide, nitrogen, water vapour, and traces of sulphur and methane, a mixture exhaled from deep within through fractures and calderas. As the mantle releases its volatiles, clouds gather into vast banks, their undersides lit faintly by the ruddy glow of molten flows far below. Cooling continues, and in time the vapour begins to condense into rain, though the drops are hot and the crust beneath is still young, dark and unstable. When they fall, they hiss on contact, etching thin mineral crusts and dissolving ions from the fresh rock. The first true interaction between persistent liquid water and solid surface begins here in short-lived intervals, between heating pulses, the beginnings of the long erosion that will shape every future continent. Basalt fractured and glassy reacts quickly, its surfaces altered to clays and secondary minerals, and these reactions draw down some atmospheric gases, changing the composition of the air by slow degrees. Chemical weathering liberates elements like sodium, calcium and silica, washing them into low-lying areas where temporary pools evaporate and form again. In these quiet basins, minerals precipitate in fine-grained layers, leaving laminated records that, if preserved, will become some of the oldest sedimentary rocks on Earth. A few of these rocks do survive, though only as fragments within younger formations, telling geologists that liquid water was stable on the surface over 4 billion years ago. The irony is quiet but sharp. Only through relentless erosion does land begin to build its character, and only through the action of water, which will later be seen as the force that breaks it down. Another soft observation is that the first rain may not have been gentle at all. Torrents and storms likely hammered the landscape, yet the net effect is a gradual smoothing, a patient chemical conversation between rock and water. A third is that much of this early crust, painstakingly altered by rain, will soon be lost to subduction, its new minerals swallowed back into the mantle to melt again. Hydrothermal systems flourish in this wet crust environment, especially along fissures where hot water circulates through fractured basalt, exchanging ions and depositing metals in veins. These systems concentrate elements like copper, zinc and gold in zones that will remain buried for eons, awaiting their future discovery. The heat from these systems is driven partly by radioactive decay in the mantle, and partly by the latent heat of solidifying magma, an enduring engine that maintains fluid flow as long as fractures remain open. As water penetrates deeper, it hydrates mantle rocks, transforming olivine into serpentine and releasing hydrogen gas, a subtle geochemical feedback that changes both rock density and the chemistry of the surrounding environment. Whether this hydration process contributes directly to the onset of modern-style subduction remains uncertain. Some models suggest it lubricates zones of weakness, making it easier for crustal slabs to sink. This is a quiet scientific mystery, its answer hidden in a time when tectonic traces are nearly all erased. The topography is low without tall mountains, for the crust is too thin and warm to support great relief, yet impact craters still mark the surface, some shallowly flooded by standing water, others filled with hydrothermal circulation. Around their edges, ejecta blankets weather into soil-like material, primitive in texture, but capable of hosting chemical gradients. Over tens of millions of years, these shallow seas and crater lakes expand and contract, with climate shifts driven by volcanic degassing and the evolving greenhouse effect. A gentle analogy forms: the surface behaves like a slow-breathing lung, inhaling as water covers more ground, exhaling as evaporation lays bare the rock again. In the absence of life, the cycle is purely physical and chemical, yet its rhythm will be familiar to every future coastline. The crust thickens incrementally as new basalt is added from below, but buoyant silica-rich magmas already begin to intrude, crystallizing into tonalate trondhjemite and granodiorite rocks that, like granite, are less dense than basalt and will come to dominate continental interiors. These TTG suites, as geologists call them, mark a turning point. Patches of crust now have the buoyancy to resist subduction, remaining as small proto-continents amidst the basaltic seafloor. They are scattered and low, separated by wide volcanic plains and shallow seas, but they represent the first real distinction between oceanic and continental crust. Isotope data from ancient zircon grains suggest that such continental-like crust exists sporadically even in the Hadean, though it is likely short-lived in most places. The paradox here is that the survival of these early patches depends as much on chance as on composition. Too close to an active subduction-like zone, and they will be swallowed. Far enough from mantle upwellings and they may endure. Volcanic arcs, if they exist yet in any recognizable form, may contribute to these patches by adding felsic magmas to the margins of thicker crust. Elsewhere, giant impactors still arrive from space, occasionally disrupting hundreds of kilometers of surface, melting it to depth, and erasing any topography that has formed. Yet even such destruction plays a role, for impact basins can become collection points for sediments and for new magmas rising to fill them. Rain continues to fall through the steamy air, its chemical work constant if slow, dissolving feldspar to kaolinite, leaching cations into runoff, and carrying the raw materials of future sedimentary sequences. In low-lying volcanic plains, sheet floods of muddy water deposit fine layers that dry crack and are buried by the next lava flow. The alternation of wet deposition and volcanic resurfacing builds a complex stratigraphy, though much of it will later be deformed beyond recognition. The cycle of weathering, transport, deposition, burial and melting begins here long before it can be recorded in the detail available to younger rocks. Only a few stable minerals, zircon most of all, carry the memory forward, tiny time capsules resistant to heat and weather. Each crystal contains isotopic ratios that tell of crustal evolution of magma sources, of the presence of liquid water, and of the slow cooling of a once incandescent world. In these quiet grains lies the faintest geological autobiography, one that speaks without haste or embellishment. The crust remains thin by modern standards on the order of tens of kilometers at most, but with each volcanic pulse, each intrusive body, each patch of preserved felsic rock, it gains resilience. The hydrosphere above and the mantle below work in long opposition, one breaking one building, and the balance between them shifts imperceptibly toward permanence. There is no single moment when the crust becomes continental in the sense it will later hold. Rather, it is an accretion of small survivals stitched together across billions of years. For now, water's touch is still new, its basins small, its permanence fragile, but the quiet truth is that the crust has begun to remember. The thin plates of the young crust begin to shift, more deliberately stirred by convective currents in the mantle, that though slower than the roiling churn of earlier ages, still carry enough heat to deform the brittle surface. Where two plates diverge, molten basalt wells, up from below, freezing into new seafloor in ridges and plateaus. Where they converge, the denser slabs founder into the mantle, returning their material to the deep. These are not yet the fully stable, long-lived tectonic systems of later Earth, but the patterns are recognizable: elongate volcanic arcs, linear fracture zones, proto-ocean basins. The spreading centers release buoyant plumes of steam and volcanic gases, while subduction-like zones recycle hydrated basalt, liberating water into the mantle wedge and producing partial melts richer in silica. These melts, lighter than their surroundings, rise through fractures and accumulate beneath the surface, feeding small felsic intrusions that begin to fortify the earliest continental fragments. The mechanical process is indifferent, yet the result is cumulative. Each cycle of formation and destruction leaves behind a slightly more buoyant, more durable crust. The irony is quiet but persistent destruction is the architect of stability, and loss is the precondition for endurance. Over time, the geometry of plate motion changes as mantle convection slows. Plates move farther without as much heat to drive them, a paradox born from cooling. The larger plates carry small patches of proto-continental crust as passengers across an oceanic matrix, colliding to create sutures marked by fault zones, ultramafic belts and fragments of ancient seafloor now stranded on land. In the heat of collision, mountain belts rise briefly before erosion levels them, their sediments carried into surrounding basins where they mix with volcanic ash and chemical precipitates. Only a few of these belts survive in recognizable form, embedded within ancient cratons as greenstone belts, remnants of oceanic crust and volcanic arcs, pressed into the heart of early continents. Their composition tells of a hotter mantle, their pillow lavas and banded iron formations capturing snapshots of a planet still experimenting with stability. A softer detail emerges in the chemistry of these rocks. Trace element patterns in basalts and komatiites show that the mantle was more depleted in some regions than others, evidence that partial melting had already reshaped its composition in localized zones. These geochemical fingerprints, preserved for billions of years, are among the few clear voices from a time when continents were scattered and small. Yet the pattern of convergence and divergence once begun will never cease. The crust becomes a participant in its own renewal, constantly exchanging mass with the mantle. A long rift's heat thins the crust, allowing a stenospheric upwelling to create new basaltic surfaces, These rift zones, later buried or sutured shut, leave subtle geophysical anomalies detectable only by the instruments of much later ages. In subduction-like zones, fluids released from the descending slab lower the melting point of the overlying mantle, generating andesitic and dacitic magmas, transitional compositions that blend the oceanic and continental traits of crust. Such magmas, when cooled slowly in the upper crust, yield tonalite trondhjemite granodiorite, assemblages key building blocks of continental nuclei. Whether this early tectonic activity resembles modern plate tectonics is debated. The rock record is too fragmentary to resolve the question definitively, and models vary from near-modern style subduction to stagnant lid regimes punctuated by catastrophic overturn. The mystery lingers because so little of the original cruise survives. Most of it has been subducted, remelted, or metamorphosed beyond recognition. What is certain is that heat loss drives motion, and motion shapes the crust into mosaics of different composition and density, some destined to survive, others to sink. The steady drift of these fragments across the planet's surface sets the stage for future supercontinent cycles, though in this era the largest landmasses are only a fraction the size of later continents. Even so, collisions between these fragments produce localized crustal thickening, creating buoyant roots that help shield them from subduction. It is another quiet irony that once crust grows thick enough, it tends to survive longer, and the longer it survives, the thicker it can become through successive events. Granite bodies light and resistant crystallize deep within these thickened zones, their large mineral grains recording slow cooling under insulating blankets of rock. Uplift eventually exposes them to weathering, their feldspars breaking down into clays, their quartz grains travelling far in rivers that meander across low-relief landscapes before reaching shallow seas. The rivers themselves are new features of this maturing crust, their channels etched by gravity and rainfall into surfaces that once shed water only in sheet floods. With rivers comes a different style of sedimentation. Point bars, deltas, and graded beds, small now, but a preview of the complex sedimentary architectures that will dominate later eras. The crust beneath these landscapes continues to move, albeit imperceptibly, to the scale of weather and water. At divergent boundaries, basaltic crust thickens into ridges. At convergent boundaries, crustal roots deepen and stabilize. In between transform faults offset segments of seafloor and continental margin alike, their horizontal motions grinding rock to fine gouge that will in time become the slick metamorphosed layers known as mylonites. Every part of this system operates slowly compared to the planet's earliest days, but fast compared to the billions of years still ahead. In the geochemical record of these processes, isotopes of strontium, neodymium, and lead provide clues to crustal recycling rates and mantle differentiation, telling of an increasingly heterogeneous Earth where no two regions share identical histories. A lesser-known detail lies in the thermobarometry of ancient metamorphic rocks, some record pressures and temperatures consistent with burial to depths of tens of kilometers, implying tectonic burial and exhumation cycles already underway. These cycles, subduction, metamorphism, uplift, are the heartbeat of a dynamic crust, and their persistence over billions of years will ensure that the surface is never static. Yet even with motion and renewal, the surface maintains long intervals of stability, especially in cratonic cores where thick lithospheric keels extend deep into the mantle, protecting them from deformation. The balance between motion at the margins and stillness in the cores defines the emerging pattern of Earth's geology. The quiet analogy is that of a slow-moving carousel, edges shifting and colliding, while the central mounts remain nearly fixed. In the background, mantle plumes still rise from deep sources, sometimes creating vast outpourings of basalt that bury whole regions under dark cooling sheets. These flood basalts, while destructive to existing landscapes, contribute to crustal growth and introduce chemical heterogeneity that will later influence mineral deposits. Above them, the atmosphere continues to change as volcanic outgassing and chemical weathering adjust the ratios of greenhouse gases. With each pulse of tectonic movement, the planet's surface becomes a little more varied, a little more layered, a little more capable of holding its form. The continents of the far future are being assembled here in pieces carried on plates that do not yet know their destinations. The process is endless and without urgency. Each collision, each rift, each volcanic arc is a single step in a path that spans eons, and the crust learns patience in its constant reshaping. Over millions of years, small buoyant patches of crust, some scarcely larger than islands, begin to harden into the stable fragments geologists will one day call cratons. These ancient cores form when repeated cycles of volcanic addition, sedimentary burial, metamorphic transformation, and tectonic thickening combine to produce lithosphere, both chemically and mechanically resistant to destruction. Beneath them, the mantle cools and stiffens into deep keels that anchor the overlying crust, extending hundreds of kilometers downward, a structure that insulates them from the convective currents, still stirring the rest of the planet. At the surface, these cratons appear unremarkable low-weathered plateaus without the drama of mountain chains, but their stability is unmatched, and their rocks preserve a record of processes erased elsewhere. The irony lies in their quietness. The most enduring land is often the least visibly dynamic. Their early growth depends on the convergence of volcanic arcs, rifted fragments, and impact-modified terrains all sutured together by granitic intrusions and metamorphic belts. The tonalite trondhjemite granodiorite suites produced in arc magmatism and partial melting of hydrated basalt dominate their composition lighter than oceanic crust, and thus less likely to be recycled into the mantle. Inclusions of older zircons within younger granitoids tell of recycled continental material, a geological memory nested within newer growth. Another soft observation is that while cratons seem immovable, their assembly is born from movement. Without relentless collisions and intrusions, the stability they embody could never arise. The sedimentary veneers draped across them in quieter intervals are thin compared to the volume of crystalline basement below, yet they carry clues about ancient atmospheres, oceans and surface temperatures, their chemical signatures recording the slow evolution of the hydrosphere. In some places, banded iron formations are interlayered with volcanic rocks, precipitated when dissolved iron in the oceans reacted with free oxygen, a process tied to localized photosynthetic activity or to oxidation from ultraviolet light in an atmosphere still lacking an ozone shield. These formations are both chemical archives and markers of change in ocean chemistry, though their precise triggers in the earliest times remain a quiet uncertainty. Around the margins of cratons, greenstone belts preserve relics of volcanic arcs, oceanic plateaus and sediments caught between colliding fragments. Their metamorphosed basalts, andesites and sediments show pillow structures and turbidites, evidence of submarine eruptions and underwater landslides in vanished seas. Some belts record ultramafic komatiites, their high magnesium content a reminder of a hotter mantle and more vigorous partial melting. Geochemists note that these belts also contain trace element signatures pointing to subduction-like processes, a suggestion that plate tectonics, or at least a proto-form of it, was already operating in patches by this time. Yet here lies another quiet paradox: the very zones that preserve this evidence are peripheral, while much of the main cratonic core holds older but more ambiguous records stripped of context by metamorphism. The cratons are not monolithic but mosaics, their components welded together under pressures and temperatures high enough to reconstitute minerals without melting the entire rock. The result is a patchwork of gneisses, schists, amphibolites, and migmatites, each representing different depths and histories of formation, all uplifted and eroded to the same subdued surface over immense spans of time. Above, the atmosphere continues to thin of greenhouse gases as chemical weathering on land draws down carbon dioxide into carbonate minerals, while volcanic degassing replenishes it at a slower rate. The balance shifts gradually, allowing surface temperatures to stabilize within ranges where liquid water remains common. Rivers become more permanent features, carving into the margins of the cratons, delivering sediments to surrounding basins that may later be accreted in new tectonic events. These rivers are narrow compared to later systems, but they bring a new dimension to erosion. Not only do they move sediments downslope, they create pathways for chemical alteration deep into rock masses, enhancing weathering far beyond the surface veneer. Gentle analogies come easily. Here the craton acts like a fortress built from collisions, and heat its walls slowly softened by streams that will never breach its heart. The interior of the craton remains tectonically quiet, but far from its core. At active margins, oceanic crust continues to founder into the mantle, generating magmas that build new continental crust. These magmas rise cool and crystallize into lighter rocks that are added to the edges of the continental nuclei, expanding their footprint. With each accretionary event, the continent grows outward in a jagged outline, only to have its protrusions later beveled down by erosion and reworked into sediments. Another irony persists: the shape of a continent is temporary, but its core can outlast entire oceans. In deep time, cratons serve as the seeds around which supercontinents will later assemble their stability, attracting suturing fragments in global cycles of assembly and breakup. The geochemical signatures of cratonic rocks, especially their depleted mantle model ages, allow geologists to trace when each segment of crust separated from the mantle. These ages cluster in certain intervals, suggesting pulses of crustal growth, perhaps linked to mantle dynamics or to external events like increased meteorite impacts. The patterns are global, but the reasons are not fully understood. Mantle plumes, changes in subduction style, or shifts in the thermal state of the planet are all candidates, none confirmed. The deep keels beneath the cratons, composed of cold dehydrated peridotite, are nearly buoyant relative to the surrounding mantle, an unusual physical property that helps them persist. Seismic imaging in the modern era reveals these keels extending far below the crust, their roots, as defining to a craton as the rock at its surface. In their earlier stages, they are formed by melt extraction, which removes heavier elements and leaves a residue that is chemically refractory and physically strong. This process not only stabilizes the craton, but also creates a mantle environment that can concentrate certain minerals, a legacy that in the far future will influence human mining. Yet in this age there is no witness to their wealth, only the slow dance of mantle and crust in mutual shaping. Overlying the craton in places are shallow seas, their waters calm compared to the turbulence of the open ocean. In these seas, sediments settle in thin sheets, carbonates where conditions permit silts and clays elsewhere, preserving in their chemistry traces of the atmosphere and hydrosphere. Some of these sediments are later buried and lithified, incorporated into the growing crust, while others are stripped away during tectonic uplift. The cycle repeats endlessly, its rhythm so slow that no single feature remains fixed, yet the cratonic core beneath persists. The quiet observation is that permanence in geology is a matter of perspective. Even the oldest rocks are temporary in the scale of the Earth's life, yet against human time they appear eternal. The continents in this moment are no more than low scattered fragments rising slightly above broad volcanic plains and shallow seas. Their future grandeur is invisible, yet already their foundations are in place. Each craton, a survivor of billions of years of heat, impact, erosion and burial. In their stillness lies the memory of the planet's earliest experiments in making land that lasts. volcanic activity remains one of the primary architects of the early continents, its influence both destructive and constructive in equal measure. Along the boundaries where plates converge, arcs of volcanoes rise above subduction zones, fed by magmas generated as seawater and sediments are drawn deep into the mantle and released as fluids that lower the melting point of surrounding rock. These magmas, richer in silica and volatiles than the basaltic melts of mid-ocean ridges, ascend slowly through the crust, cooling into granitic bodies, or erupting in stratovolcanoes that shed layers of ash pumice and lava over wide areas. Over millions of years, such arcs stitch new felsic crust onto the edges of protocontinents, thickening them and increasing their buoyancy. The irony is that eruptions which bury landscapes in ash also create fertile soils that in a much later world will nourish life. Here they simply contribute minerals to rivers and seas, altering water chemistry and seeding sediments. Another quiet observation is that volcanic chains so fleeting in human terms can endure for tens of millions of years in geological time, only to be dismantled and recycled by the same processes that formed them. Beyond arcs, large igneous provinces erupt episodically, when mantle plumes reach the base of the crust, releasing vast floods of basalt that can cover hundreds of thousands of square kilometers in a matter of centuries. These basalt sheets bury older terrains, reset weathering processes, and contribute heat and volatiles to the atmosphere, temporarily tipping climate conditions toward warmer, wetter states before chemical weathering of the fresh rock draws down greenhouse gases again. The paradox here is that such catastrophic events can ultimately stabilize climate over long scales, a feedback loop tied to the chemistry of silicate weathering. In subduction zones, partial melting not only produces felsic intrusions, but also contributes to the recycling of oceanic crust into the mantle, a cycle that maintains the chemical diversity of both crust and mantle over billions of years. Sediments scraped from the subducting slab are plastered onto the overriding plate in accretionary wedges, where they are folded, faulted, and metamorphosed. These wedges, later uplifted and eroded, add more fragments to the continental margin, further enlarging the landmass. It is in these environments that some of the oldest known metamorphic rocks form their mineral assemblages, recording pressures and temperatures that speak of deep burial and subsequent exhumation. The presence of blue schists and eclogites in much younger rocks will one day be used as definitive proof of modern-style subduction. Here their absence or rarity leaves open the quiet mystery of exactly when subduction in its current form began. Inland from volcanic arcs, the heat of intruding magma bodies metamorphoses surrounding crust into aureoles of altered rock, creating mineralogical gradients that reveal the depth and intensity of magmatic processes. These zones are evidence of crustal thickening and heating conditions that promote the growth of stable continental interiors. Rivers draining volcanic highlands carry a mix of volcanic lastics, weathered minerals, and dissolved ions into low-lying basins, where they settle into stratified layers that will over time lithify into sedimentary rocks. Such basins may form behind arc systems in back-arc settings or in fallen positions ahead of colliding blocks, each type preserving different aspects of the crustal and tectonic environment. Over longer timescales, some basins are inverted by renewed compression, their sediments deformed and uplifted into new mountain belts, further adding to continental mass. Mantle plumes remain a major influence their upwellings, producing not only flood basalts, but also silicic volcanism, when mantle-derived magmas pond beneath continental crust and trigger partial melting of the lower crust. The resulting rhyolitic and granitic compositions contribute more buoyant material to the continents, reinforcing the long-term trend toward lighter, thicker crust in continental interiors. A gentle analogy might be that of a sculptor repeatedly adding clay to a form, each addition rough at first, but later smoothed by weathering and erosion. Between volcanic episodes, erosion and chemical weathering work steadily to redistribute materials. On land, volcanic rocks break down into clays, iron oxides, and quartz grains, feeding deltas and shorelines. In shallow seas, volcanic ash layers settle and are altered to bentonite clay that will be a subtle marker for geologists tracing ancient eruptions. Where rivers enter quiet waters, their load of fine sediment settles into laminated mudstones, while coarser sands drop out earlier to form beaches and bars. These environments, though small in scale compared to later continental margins, represent the earliest persistent sedimentary systems tied to continental sources rather than purely oceanic ones. Another irony emerges here: the same volcanoes that build land also fuel the processes that dismantle it, ensuring that no landscape remains unchanged. The composition of volcanic products evolves with time as mantle temperatures decline, and the proportion of recycled crustal material in magmas increases. Basalts become less ultramafic andesites, and dacites more common granites more abundant in continental interiors. This chemical evolution reflects both mantle cooling and the growing efficiency of crustal recycling through tectonics. Even without complete modern-style plate tectonics, the interplay of plume magmatism, arc volcanism, sedimentation, and metamorphism produces a crust that is already chemically distinct from the mantle, and from the oceanic crust forming at spreading centers. Geophysical contrast between continental and oceanic lithosphere deepens, setting the stage for future geodynamic patterns. At the planetary scale, the heat budget is slowly shifting. Radiogenic isotopes decay, reducing internal heat production, while the thickening crust and growing continents change the patterns of heat flow from the interior. The long-term consequence is a gradual slowdown in mantle convection, which will lengthen tectonic cycles and alter the frequency of volcanic events. Yet in this early era, the system is still active enough that volcanic additions remain a dominant driver of continental growth. Volcanic gases rich in water, vapor carbon dioxide, sulfur dioxide, and trace compounds continue to influence atmospheric composition. Chemical weathering of volcanic rocks consumes carbon dioxide, feeding a planetary feedback that modulates climate over tens of millions of years. The oxygen content of the atmosphere remains extremely low, but localized oxidative processes occur in surface waters, sometimes visible in the mineral coatings of weathered volcanic rocks. These localized oxidized zones are fleeting, erased by burial or erosion, but they hint at the capacity of surface processes to alter planetary chemistry well before the Great Oxidation Event. In the long rhythm of crustal development, volcanic processes remain inseparable from tectonic sedimentation and weathering. Each eruption, each intrusive body, each arc or plume contributes not just rock, but chemical signatures, structural patterns, and thermal imprints that will be inherited by later crustal generations. The continents at this stage are an uneven patchwork of volcanic highlands, shallow sedimentary basins, metamorphic belts, and stable cratonic cores, each part reflecting a different blend of magmatic and tectonic processes. Their outlines are irregular, and their elevations modest, but their buoyancy and resilience are growing. In their continued assembly, there is no sense of finality, only the patient accumulation of material cycle by cycle, eruption by eruption, until the land as a whole begins to assert its presence against the ocean. The continental fragments, still modest in size, begin to drift slowly across the planet's surface, carried on plates whose motions are driven by the waning heat of the mantle, but still guided by deep currents and plume upwellings. The movement is slow enough to seem motionless on any human timescale, yet over millions of years, collisions and separations reshape the geography of this early Earth again and again. Fragments converge to form larger landmasses, then rift apart into smaller pieces, their margins outlined by volcanic arcs, rift valleys, and shallow seas. These shifting configurations allow different crustal blocks to share histories, welding together material of varied age and composition. At collision zones, mountains rise briefly low by modern standards, for the crust is still warm and less rigid, then are rapidly eroded by rainfall and rivers, their sediments spread into surrounding basins. These basins in turn may be buried by younger volcanic flows or folded into new mountain belts in subsequent tectonic events. The irony is that the same collision that raises a range also begins the process of dismantling it, as highlands shed material to the seas that may later be accreted back onto another margin. A softer observation comes from the study of metamorphic belts, which show that crust can be buried to great depths and later return to the surface carrying minerals that form only under high pressures and temperatures. Even in this early era, such cycles hint at the recycling and renewal that will define the crust's long-term history. The gradual drift of land masses alters ocean circulation, which in turn affect climate patterns. Shallow epicontinental seas flood low-lying interiors, their warm waters encouraging the deposition of carbonates, cherts, and fine clastics, all of which will contribute to the chemical and structural diversity of the crust. These seas are dynamic environments, expanding and contracting, with tectonic uplift and subsidence, and with changes in global sea level linked to the thermal state of oceanic crust. A quiet paradox emerges: the continents grow, in part because they are surrounded by oceans which erode and redeposit their margins in ways that promote long-term preservation of buoyant material. The mechanical processes at plate boundaries remain varied. In subduction zones, oceanic lithosphere sinks into the mantle, generating volcanic arcs and adding new felsic crust to continental margins. In rift zones, mantle upwelling produces basaltic magmatism that can eventually evolve into more silica-rich compositions through fractional crystallization and crustal assimilation. Transform boundaries accommodate horizontal motion, grinding crust to fine rock flour that lubricates further movement. Each of these settings contributes uniquely to the balance of crustal destruction and creation, a balance that has since the earliest times tilted slowly toward net growth of continental material. The land masses are not yet the stable supercontinents of later eons, but their slow dance across the globe is the beginning of the long supercontinent cycle. While reconstructions of these earliest configurations remain uncertain, isotope data suggest that there were episodes when multiple cratons came together into larger composite continents, only to break apart again. These events leave subtle geochemical fingerprints in detrital zircons, which record both the age of the original crust and the age of its reworking. The very fact that such zircons are found in sedimentary rocks of widely separated modern cratons is evidence that once they were neighbours. Another quiet mystery lingers in the distribution of greenstone belts and high-grade gneiss terrains. Why do some cratons preserve abundant relics of oceanic crust, while others are almost entirely felsic? The answer may lie in differences in tectonic setting, mantle, heat flow, or even the thickness of lithospheric keels, but the record is too incomplete to be definitive. The continental interiors removed from active margins experience long intervals of stability, allowing weathering to deepen and soils to form. These soils are rudimentary compared to modern equivalents lacking organic matter and structured horizons, yet they alter the crust chemically by leaching mobile elements and concentrating more resistant minerals. Erosion rates are slower here as the topography is subdued, and tectonic uplift minimal. In contrast, margins are sites of intense activity, volcanism, sedimentation, deformation, all of which contribute to the addition of new crust. Rivers draining high relief areas deliver vast loads of sediment to continental shelves, where they accumulate in thick wedges that may later be buried and metamorphosed. Over time, these wedges can be accreted to the continent during further collisions, effectively transferring material from one margin to another. The irony is that the edges of continents, the most unstable and short-lived parts, are often where most of the new continental material is generated. Mantle plumes occasionally disrupt this steady tectonic rhythm, producing large igneous provinces that can straddle continental interiors or erupt through rift zones. When plume heads interact with continental crust, they can generate enormous volumes of silicic magma, producing volcanic plateaus and intrusive granitic complexes that permanently increase crustal thickness and buoyancy. These events are rare on the scale of millions of years, but significant in shaping the structure and chemistry of the crust. The geochemical signatures of such plume-related magmatism enrichment in incompatible elements, distinct isotope ratios will be preserved in the rocks for billions of years, markers of a process that adds to the continents from below rather than at their margins. In the global context, the slow amalgamation and dispersal of continents influences the distribution of shallow marine habitats, the cycling of elements between the crust oceans and atmosphere, and the long-term thermal evolution of the mantle. The continents act as insulating lids, reducing heat loss in the regions they cover and focusing mantle convection in the oceans. This feedback between surface configuration and internal dynamics will continue to shape Earth's behavior for the rest of its history. By now, the chemical distinction between continental and oceanic crust is well established. Continental crust is thicker, more buoyant, more silica-rich, and older on average, while oceanic crust remains thin, dense, mafic, and short-lived. This dichotomy ensures that continental material once formed has a much higher chance of survival than oceanic lithosphere, which is continually recycled at subduction zones. The result is a slow but persistent growth of continents over geological time, punctuated by episodes of crustal loss during massive tectonic or magmatic events. In the midst of this weathering and erosion continue their quiet work. Rain rivers wind and waves strip material from highlands, transport it to lowlands and seas, and bury it in sediments that in time will be transformed into new rock. Even in tectonically quiescent regions, the crust is never truly at rest. It is always engaged in the long cycle of breakdown and rebuilding, a process as integral to its growth as the magmatism at plate boundaries. The continents, though still far from their eventual forms, are becoming enduring features of the planet. Their cores hold rocks that have survived the violence of early Earth, their margins constantly reshaped by the meeting and parting of plates. Every zircon grain, every band of gneiss, every layer of metamorphosed volcanic rock carries a fragment of this history, a record of a world that has always been in motion, and yet has always been building toward the stability we now see in its oldest stones. At the boundaries where oceanic crust sinks into the mantle, the quiet but relentless process of subduction continues to reshape the continents from below. Older, denser seafloor bends downward along deep trenches, carrying with it sediments, hydrated minerals, and fragments of oceanic crust into zones of intense pressure and temperature. As these materials descend, water and other volatiles are released into the overlying mantle, wedge lowering its melting point and generating magmas of intermediate to felsic composition. These magmas, enriched in silica, sodium, and potassium, are less dense than the surrounding rock and slowly rise toward the surface, cooling into plutonic bodies or erupting in volcanic arcs that fringe continental margins. Over millions of years, the accumulation of such magmas thickens and stabilizes continental crust, adding buoyant material that resists recycling into the mantle. The irony is that the destruction of oceanic crust at these margins is what fuels the growth of continents themselves. Subduction zones are also places of sedimentary accretion where material scraped from the descending slab is plastered onto the overriding plate, forming chaotic melanges and folded wedges of turbidites, cherts, and volcanic lastics. These accretionary complexes, though geologically messy, are vital in transferring marine sediments into the continental crust, preserving chemical signals from the oceans and atmosphere at the time of their deposition. A softer observation is that sediments which began as particles eroded from older continents can through subduction and accretion return home transformed into rock once more. In the deepest parts of these zones, basaltic crust is metamorphosed into eclogite, a dense rock that helps pull the slab further downward, sustaining the process. The conversion of basalt to eclogite releases additional fluids, feeding more melting in the mantle, wedge a feedback loop that keeps subduction active as long as density contrasts and gravitational pull persist. Another quiet irony lies in the fact that eclogite born in the dark, crushing depths of subduction zones can reappear at the surface if tectonic forces exhume it quickly enough, carrying garnet and omphacite crystals that speak of pressures equivalent to burial beneath more than 100 kilometers of rock. Subduction zones also influence the mechanical and chemical architecture of the continents far inland. Magmatic intrusions hundreds of kilometers from the trench mark the inland reach of arc magmatism, while compressional forces create broad fallen basins where sediments accumulate in thick successions. These basins, later buried and lithified, record the interplay of mountain building and erosion in layers of sandstone, shale, and limestone. Their eventual deformation in younger orogenies will recycle them yet again into the crustal fabric. The geothermal gradients near active subduction zones are steep, and metamorphism of crustal rocks produces mineral assemblages that lock in temperature-pressure histories. These histories, read by geologists in the far future, will become some of the clearest evidence for the persistence of subduction through deep time. Whether subduction as we know it today began early or emerged gradually remains a point of scientific debate. The scarcity of unaltered rocks from the Archean leaves room for multiple interpretations. Some propose that episodic plume-driven overturns preceded continuous plate tectonics, while others see signs of steady-state subduction in the geochemistry of ancient volcanic rocks. The truth may lie somewhere in between a gradual transition, in which localized subduction zones appeared first, then linked into a global network. Regardless of its origin, subduction sets in motion a recycling system that continually modifies continental crust. Each pulse of arc volcanism adds new granitic material. Each episode of sediment accretion binds ocean floor detritus into continental frameworks, and each deep burial and exhumation cycle reshapes the mineralogy and chemistry of the crust. Over tens to hundreds of millions of years, this process produces composite continents whose margins are a patchwork of terrains, each with its own geological history. These terrains can be volcanic arcs, fragments of oceanic plateaus, microcontinents, or sedimentary prisms all stitched together along fault zones and sutures. The stitching is not seamless. Seismic waves will one day reveal deep scars beneath the surface boundaries where the crust retains its internal complexity long after the surface appears unified. In the volcanic arcs above subduction zones, the interplay of magma composition, volatile content, and eruption style determines the surface expression of crustal growth. Explosive eruptions build stratovolcanoes whose layered structure mirrors the cycles of eruption and repose, while effusive eruptions spread thick lava flows that cool into resistant plateaus. The ash from explosive events can travel hundreds of kilometers, settling in fine layers that later harden into tuff and rhyolite, adding chemically evolved rock to the crust. Over time, these layers become part of the continental interior through tectonic transport and uplift. Volcanic gases, particularly carbon dioxide and sulfur dioxide, also influence atmospheric chemistry. The weathering of fresh volcanic rocks on land consumes carbon dioxide, contributing to long-term climate regulation, while the release of sulfur aerosols can temporarily cool the planet by reflecting sunlight. These climate feedbacks operate on timescales far longer than the eruptions themselves, illustrating how tectonic processes affect the entire Earth system. Sediments eroded from volcanic arcs are delivered by rivers to marine basins, where they are deposited in thick sequences. These sequences, later buried and metamorphosed, contribute to the structural and chemical makeup of the continental crust. Even the smallest grains in these sediments carry isotopic evidence of their source rocks, allowing future scientists to trace their origins back to specific magmatic events. In this way, the products of subduction magmas, sediments, metamorphic rocks, become woven into the deep and enduring fabric of the continents. Subduction is also responsible for concentrating economically important minerals within the crust. Arc magmas and associated hydrothermal systems deposit copper, gold, molybdenum and other metals in veins and disseminated ore bodies, locked away in the crust for eons. In the present there is no witness to their value, only the quiet accumulation of chemical wealth in zones that will one day be quarried by intelligent hands. The persistence of subduction depends on the contrast between the density of oceanic lithosphere and that of the underlying mantle. As the planet cools, oceanic plates grow thicker and denser, with age ensuring their eventual descent at trenches. The continents, more buoyant and thicker, generally avoid subduction, making them the long-term archive of Earth's geological memory. Over time, subduction zones migrate, consuming old ocean basins and creating new ones, shifting the positions of continents in a global cycle that spans hundreds of millions of years. This cycle, known in its later form as the supercontinent cycle, ensures that the continents are repeatedly assembled and dispersed, their margins renewed with each iteration. The quiet observation is that while the continents seem fixed, their outlines are temporary sketches drawn by subduction's steady hand. In the deep rhythm of this process, there is no final state, only an ongoing conversation between the mantle and the crust, mediated by the slow descent of plates into the depths. Every trench, every arc, every accreted wedge is another line in the story, written in the language of stone and preserved for those who will later learn to read it. In the heart of the continents, far from the restless margins where subduction feeds volcanoes and mountain belts, buoyant magmas rich in silica rise slowly through older crust, cooling into the pale, coarse-grained rocks that will come to define much of the continental interior. This granite, formed from melts of both crustal and mantle, origin crystallizes deep underground, insulated by kilometers of overlying rock that allow mineral grains to grow large and interlocking. The process is deliberate, and prolonged magma ponds in chambers fractionates, assimilates surrounding material and cools in a slow retreat of heat to the surface. These granitic masses, once solidified, are mechanically strong and chemically resistant, adding volume and stability to continental crust. The irony is that while granite is emblematic of enduring land, it originates from magmas that were once mobile fluid and hot enough to displace solid rock. The formation of granite is tied to the evolution of crustal composition. Early Earth's higher mantle temperatures favoured mafic compositions, but as the crust differentiated and recycled, silica-rich magmas became more common. Water introduced into the crust through subduction and weathering lowers the melting point of rocks, making granitic magmas more likely to form. This interplay of composition, water content and heat flow marks a transition toward continents dominated by felsic rocks. Another quiet observation is that granite, though it forms out of sight in the deep crust, shapes the surface for billions of years by creating regions of buoyant lithosphere that resist subduction and stand high as shields and plateaus. Granitic terrains weather differently from basaltic ones, breaking down into sand rich in quartz, feeding long rivers and beaches with material that will be recycled into sandstones. The durability of quartz ensures that it survives multiple cycles of erosion and deposition, becoming one of the most persistent minerals in the sedimentary record. Within the granite itself, accessory minerals such as zircon and monazite hold isotopic clues to the timing of crustal growth and the sources of the magma, providing a geological memory that endures even when the host rock is eroded. Large granite batholiths often form in regions of crustal thickening, such as continental collision zones, and volcanic arcs where heat from intruding magmas and radioactive decay in the crust combine to produce partial melting of lower crustal rocks. These batholiths can extend for hundreds of kilometers, their roots disappearing into the deep crust, and their emplacement changes the thermal and mechanical state of entire regions. Once exposed at the surface through uplift and erosion, granites become a hallmark of continental interiors, their light color reflecting sunlight, their coarse texture resisting rapid weathering. In ancient cratons, granitic terrains alternate with belts of metamorphic and volcanic rock, the boundaries between them marking sutures, shear zones, and ancient rifts. Over geological time, these granites are themselves subject to metamorphism, recrystallizing under heat and pressure into gneiss, yet even in this transformed state they retain their buoyancy and contribute to crustal stability. The slow unroofing of granitic plutons, as erosion strips away overlying rock, is another paradox of geological time. What was once buried deep now stands at the surface, while the surface that once existed has been lost to erosion and burial elsewhere. The exposure of granite releases minerals that influence soil chemistry and sediment composition, feeding cycles of deposition that will in time produce new crustal material through lithification and metamorphism. In some places, granitic magmas intrude directly into volcanic arcs, freezing before they can erupt, and leaving no volcanic expression at the surface. In others, they erupt as rhyolite, producing explosive ash flows and ignimbrites that blanket wide areas. These felsic volcanic rocks share the chemical traits of their plutonic counterparts, but are more vulnerable to erosion, often disappearing from the geological record unless quickly buried. The presence of granite in the crust affects its physical properties on a large scale. Continental lithosphere with a high proportion of granite is less dense and thicker than surrounding oceanic lithosphere, enabling it to ride higher on the mantle and form elevated plateaus. This elevation influences atmospheric circulation, precipitation patterns, and erosion rates, creating feedback loops between tectonics, climate, and surface processes. In a quiet way, granite not only records the history of the crust, but also helps direct the evolution of landscapes. The emplacement of granite is often accompanied by mineralizing fluids that move through fractures, depositing veins of quartz, feldspar, and sometimes metals such as tin, tungsten, and uranium. These mineral deposits are a byproduct of magmatic differentiation and hydrothermal circulation, concentrating elements that are otherwise scarce in the crust. While in this early Earth, there is no observer to recognize their significance, their formation is an inevitable consequence of the physical and chemical principles governing magma evolution. Over millions of years, erosion exposes these deposits, and weathering liberates their contents to be carried away in sediments or redeposited elsewhere. Granite's contribution to continental growth is not solely in volume. It also increases the chemical diversity of the crust. Felsic rocks are enriched in incompatible elements, those that do not fit easily into the crystal structures of common mantle minerals, and thus act as long-term reservoirs for these elements in the crust. This enrichment affects subsequent magmatism as melting of granitic crust yields magmas with different compositions from those derived from basaltic sources. Over repeated cycles of melting and crystallization, the crust becomes more compositionally varied, capable of producing a broader range of rock types and mineral deposits. This diversification is a slow but profound shift, one that sets continents apart from the relatively uniform composition of the oceanic crust. In regions where granites have been exposed for long periods, weathering produces thick regoliths rich in kaolinite and other clay minerals. These weathering profiles can extend tens of meters below the surface, recording ancient climates and the stability of the underlying crust. In later geological periods, such profiles may be buried and preserved, providing a direct window into surface conditions from deep time. Their preservation is yet another quiet irony, formed by the destruction of rock they endure only when shielded from further erosion by new deposits. The gradual accumulation of granite and its derivatives increases the volume and buoyancy of the continents, further insulating them from destruction in subduction zones. This insulation allows them to persist and grow, serving as long-term platforms for the deposition of sediments and the assembly of supercontinents. In this way, granite is both a product and a driver of continental stability, a feedback that will keep the continents above sea level for much of the planet's history. Though invisible from space at the time of its formation, the spread of granite through the crust is one of the most significant developments in Earth's geological evolution, anchoring the continents in a way that basalt alone could never achieve. In the stillness of the cratonic interiors, where granite weathers under slow rains and wind, the land seems eternal, yet every grain of quartz in a distant beach may have begun as part of a granite pluton deep underground. The story of granite is the story of continents learning to endure their foundations, set in pale crystalline stone that will outlast oceans, mountains, and perhaps even the surface itself. Along the margins of continents, where rivers meet the sea and waves grind against the land, the quiet work of sedimentation begins to leave its mark on the geological record. Mountains and highlands, raised by collisions or volcanic arcs, shed their material through the combined forces of weathering mass, wasting and flowing water. Coarse gravels and sands tumble quickly into nearby basins, while finer silts and clays remain suspended, travelling farther before settling into quieter waters. These sediments accumulate in deltas, floodplains, continental shelves, and deep marine fans, forming thick-layered deposits that will one day be buried, compacted, and lithified into new rock. The irony is that while erosion wears down the continents, it is also a primary mechanism by which they grow, for sediments can be returned to the crust through accretion at subduction zones, or by burial and metamorphism within continental interiors. In these early times, sedimentary layers are often interrupted by volcanic flows or intrusions, preserving a record of alternating calm and upheaval. A softer observation is that the most delicate laminations of silt laid down in still water may survive for billions of years if protected by later burial, even as entire mountain ranges are erased. The chemistry of sediments reflects both their source and the environment in which they were deposited. Quartz-rich sands point to prolonged weathering of felsic rock such as granite, while feldspar-rich sands suggest more rapid erosion from nearby highlands. Clays and mudstones form from the chemical breakdown of feldspars and mafic minerals, their composition altered by the presence of dissolved ions in surface waters. In shallow marine settings, carbonates precipitate directly from seawater, or are built by microbial mats, adding another dimension to the sedimentary record. Even without abundant life, the interaction of water chemistry and minerals produces distinctive layers that mark environmental conditions at the time of deposition. These sedimentary systems are shaped by the geometry of the continental margin. In tectonically active regions, steep gradients and rapid subsidence create deep basins capable of holding thick sedimentary successions, while in more stable areas, broad shelves encourage the spread of thin, laterally extensive layers. Over time, these deposits may be buried beneath younger sediments intruded by igneous rocks, or metamorphosed into schist quartzite and marble, transforming them while preserving some memory of their origin. Another quiet irony lies in the fact that sediments often travel far from their source before becoming rock, meaning that a grain of sand in one continent's interior may have begun as part of a mountain on another. Rivers act as the principal conveyors in this system, carving valleys and channels into the land and delivering their loads to deltas, where distributary networks fan out into the sea. These deltas are dynamic features shifting position, as channels are abandoned and new ones cut, building lobes of sediment that push the shoreline outward. In the geological record, such progradation is seen in coarsening upward sequences, mud below sand above marking the gradual advance of land over sea. In deeper waters, turbidity currents triggered by storms, earthquakes, or rapid sediment loading rush downslope, depositing graded beds that become the flysch of ancient mountain belts. These submarine flows are powerful enough to carry boulders, yet their deposits, once lithified, can appear as fine as ordinary sandstone. In the context of continental growth, sedimentation plays two roles. It stores eroded material in basins where it can be preserved from further weathering, and it creates the raw material for new crustal rock through burial metamorphism and magmatic recycling. In subduction zones, sediments scraped from the ocean floor are added directly to the continental margin, sometimes forming thick accretionary prisms that stabilize and broaden the continent's edge. In other cases, sediments are carried deep into the mantle, with the subducting slab where they contribute to the chemistry of arc magmas and re-enter the crust in new form. Over millions of years, these cycles leave their imprint in the isotopic signatures of continental rocks, recording the repeated addition of sedimentary material to the continents. The preservation of sedimentary basins depends on tectonic setting. Rift basins form where continents stretch and thin, creating elongated depressions that fill with sediments and volcanic material. Foreland basins develop ahead of advancing mountain belts, subsiding under the load of thrust sheets and sediment. Intracratonic basins form in the interiors of stable continents, their origin still partly mysterious, but likely tied to subtle changes in lithospheric density and mantle dynamics. In all cases, these basins act as archives of erosion, climate, and tectonics, storing information about surface processes in the deep geological past. Over time, burial transforms loose sediments into rock. Compaction squeezes out pore water, while minerals precipitated from circulating fluids cement grains together. In deeper settings, heat and pressure drive metamorphism, reorganizing minerals into denser, more stable forms. Shales become slate, then phyllite, then schist. Sandstones become quartzite, limestones become marble. These transformations not only strengthen the rocks, but also lock in mineral assemblages that record the conditions of their formation. When such rocks are later uplifted and exposed, they tell a story of cycles repeated countless times. A gentle analogy can be made: sedimentary layers are the pages of a book the earth is always writing and rewriting each burial, adding a new chapter, while older ones are pressed and altered into different forms. The movement of continents ensures that few pages remain in place forever, yet enough survive to piece together the evolving history of the crust. The chemical weathering of sediments themselves adds another dimension to continental evolution. When exposed, sedimentary rocks are often more easily eroded than igneous or metamorphic ones, returning their minerals to rivers and oceans where they may be redeposited or incorporated into chemical precipitates. This feedback loop links erosion, sedimentation, and crustal growth in a continuous cycle. In the long view, sedimentation is as essential to the persistence of continents as the magmatic processes that add new material from below. Without the storage and recycling of sediments, much of the eroded continental mass would be lost to the mantle, and the chemical diversity of the crust would diminish. Instead, sediments act as both a reservoir and a vehicle for the return of material to the continents, ensuring that even what is worn away can come back in another form. The continents shaped at their edges by these deposits grow outward in irregular fringes that may later be smoothed or broken by tectonic forces. In quiet interiors, sedimentary rocks accumulate in layers that may lie undisturbed for hundreds of millions of years, until a new pulse of tectonics uplifts them into mountain belts or drops them into deep basins again. The steady interplay between erosion and deposition, loss and return gives the continents their resilience, a resilience that is not static but maintained by constant movement. Every grain of sand, every flake of clay, every carbonate crystal is part of a journey that links the highest peaks to the deepest basins and back again, weaving the continents from the debris of their own destruction. The outline of the continents is shaped not only by the processes at their margins, but also by the steady rise and fall of global sea levels, which advance and retreat across low-lying areas in cycles that play out over millions of years. These fluctuations are driven by changes in the volume and density of oceanic crust, the thermal state of the mantle, and the formation or breakup of supercontinents, all of which alter the capacity of ocean basins. When mid-ocean ridges are especially active, hot buoyant crust displaces seawater onto the continents, flooding vast areas in shallow epicontinental seas. In quieter tectonic intervals, cooler, denser oceanic crust allows the oceans to recede, exposing wide coastal plains and connecting once isolated landmasses. These transgressions and regressions leave their signature in layered sedimentary sequences that alternate between marine and terrestrial deposits, marking the repeated expansion and contraction of seas across the land. The irony is that such cycles, seemingly transient, can reshape continental margins more profoundly than some mountain-building events, creating or erasing entire ecosystems and sedimentary environments. In the geological record, these changes are captured in the phase shifts of sedimentary rocks, limestones grading into shales, shales into sandstones, each transition telling of an ancient shoreline migrating inland or retreating seaward. During transgressions, carbonate platforms often flourish in warm, shallow waters, producing thick sequences of limestone and dolostone that can later be metamorphosed into marble or recrystallized into coarser forms. Even without abundant life, chemical precipitation from seawater leaves behind distinctive mineral assemblages that reveal the chemistry of ancient oceans. In regressions, rivers extend their channels across exposed shelves, cutting valleys and delivering sediment far beyond the former shoreline. These sediments fill low-lying basins and deltas, creating thick clastic wedges that can be preserved for hundreds of millions of years. The soft observation here is that sea level is as much a tectonic signal as a climatic one, its changes reflecting deep processes in the mantle as much as conditions at the surface. Tectonic uplift and subsidence also play a role in shaping the interaction between land and sea. In fallen basins formed ahead of mountain belts, subsidence outpaces sedimentation, creating deep water environments even within continental interiors. In contrast, broad swells in the lithosphere can elevate regions hundreds of kilometers from a plate boundary, allowing erosion to strip away overlying sediments and expose ancient crust. These vertical motions, though slow, can redirect rivers, alter sedimentary pathways, and change the distribution of depositional environments. Another quiet irony is that the continents, which appear fixed and solid, are constantly shifting not only laterally, but vertically, rising and sinking on timescales too long to perceive yet short enough to leave a complex stratigraphic record. The advance and retreat of the seas also influence the chemical evolution of the crust. Marine transgressions bring salt water into contact with continental rocks, promoting chemical weathering and the exchange of ions between land and ocean. Minerals in flooded soils can dissolve and reprecipitate, locking new chemical signatures into the crust. Likewise, the burial of organic-rich sediments in marine basins alters the long-term carbon cycle, sequestering carbon that may remain locked away for billions of years unless later tectonic events expose and oxidize it. On a global scale, these processes interact with tectonic and magmatic activity to modulate atmospheric composition, linking the evolution of the continents to the stability of climate. In the shallows of epicontinental seas, wave action and currents sort sediments into patterns that can persist in the rock record long after the sea has retreated. Crossbedding in sandstones, ripple marks in siltstones, and mud cracks in shales, all record moments when the balance between deposition and erosion shifted in response to changing water depth. These physical structures are subtle, yet enduring clues often preserved when more obvious surface features have long vanished. As the continents grow and change, shape, the distribution of shallow seas shifts as well, influencing ocean currents and the global distribution of heat. Narrow seaways between landmasses can channel currents and affect climate far from their location, while the opening of broad ocean basins allows more even distribution of heat between hemispheres. Such changes, though primarily recorded in the arrangement of continents and sediments, are part of the same deep time processes that control crustal growth and recycling. Another paradox emerges in the persistence of certain low-lying continental regions, such as broad shelves that seem perpetually vulnerable to flooding, yet survive as stable geological features for billions of years. These areas, underlain by thick, buoyant crust, are not easily destroyed by tectonics, and their repeated submergence and exposure act as a natural archive of sea level change. In the interiors of continents far from the shifting margins, the sedimentary record of sea level change is subtler but no less important. Shallow lakes and inland seas form and vanish with changes in climate tectonics and hydrology, leaving behind evaporate deposits, fine-grained lacustrine shales, and occasional carbonate layers. These deposits can be interbedded with volcanic ash layers from distant eruptions, providing time markers that allow correlation across vast regions. Over millions of years, such sequences are buried, lithified, and sometimes metamorphosed, preserving the imprint of ancient inland waters in rocks that now stand high above sea level. The vertical motion of continents, driven by the balance between erosion, sediment loading, and mantle dynamics, creates further complexity in the sedimentary record. Areas that were once basins can be uplifted into plateaus, while former highlands can sink beneath the sea. This interplay of uplift and subsidence determines where sediments accumulate and where older rocks are exposed to weathering, influencing both the growth and the recycling of continental crust. The quiet observation is that continents are not static platforms upon which other processes play out. They are themselves active participants in shaping their own margins and interiors. As supercontinents begin to assemble in the deep future, the distribution of epicontinental seas will change again, creating new patterns of sedimentation and erosion. The assembly of land masses into a single large continent alters mantle convection, increases the height of continental interiors, and changes the distribution of climates across the globe. When such a supercontinent eventually breaks apart, newly flooded margins will form, beginning the cycle anew. In each iteration, the rise and fall of sea level, the shift of shorelines, and the movement of sediments will continue to leave their mark on the evolving crust. These patterns, repeated across billions of years, weave a stratigraphic fabric that, when read carefully, tells not just of changing seas, but of the deep geodynamic forces that shape the continents themselves. In the oldest parts of the continents, the cratonic shields stand exposed, their ancient rocks weathered into broad, low landscapes where the underlying structure is written plainly in stone. These shields are composed of metamorphic and igneous rocks that have survived for billions of years, some dating back to the Hadean, and they form the geological core of the continents. The surface expression is subdued rolling hills, gentle ridges, wide plains, but beneath lies a lithosphere unusually thick and buoyant, anchored by mantle keels that extend far deeper than those beneath the younger crust. The irony is that these ancient terrains, seemingly the most unchanging, are the result of countless cycles of change in their earliest histories: collisions, magmatism, erosion, burial, and exhumation, repeated until the crust reached a composition and structure able to resist destruction. Within these shields, greenstone belts stand out as narrow, elongated zones of metamorphosed volcanic and sedimentary rocks, folded and faulted between blocks of tonalite, trondhjemite, granodiorite gneiss. The greenstones record volcanic arcs, oceanic plateaus, and sedimentary basins of early Earth, their preservation due to being trapped and welded into the surrounding felsic crust during continental growth. Pillow lavas in these belts, once extruded onto the seafloor, are now frozen in stone, their rounded forms a memory of an ancient ocean. Interlayered with the lavas are banded iron formations, chemical precipitates of iron oxides that speak of changing ocean chemistry, possibly tied to early oxygen production or to photochemical reactions under a weaker sun. These deposits are quiet reminders of a world whose atmosphere and oceans were still in chemical flux. The gneisses that surround the greenstone belts preserve a deeper record, their course banding the result of high-grade metamorphism and partial melting. Some contain inclusions of even older rocks, xenoliths carried upward from deeper crustal levels that push the known record of continental material further back in time. These inclusions often hold zircons whose isotopic compositions reveal early episodes of crust formation, reworking, and differentiation. The softer observation here is that the oldest evidence for continents often lies within rocks that have themselves been reformed multiple times, each event overwriting, but not fully erasing what came before. The stability of the shields owes much to their keels, which are chemically depleted and mechanically strong, making them resistant to both melting and deformation. This stability has allowed them to persist through the assembly and breakup of multiple supercontinents, enduring mantle plume events and major orogenies with little fundamental change to their cores. Even so, their surfaces have not been immune to erosion. Over billions of years, weathering has worn them into peneplains, low-relief surfaces near sea level, only to have them uplifted again by mantle-driven buoyancy, or by isostatic rebound following glaciations in much later eras. Each uplift exposes fresh rock to weathering, beginning the slow cycle anew. Sediments eroded from the shields are often quartz-rich, their source rocks having lost more soluble minerals to prolonged chemical weathering. These sediments, carried by rivers and winds, spread far across continental interiors and margins, contributing to sandstones and quartzites that themselves can be recycled into new crustal material. In some cases, sedimentary cover has protected shield rocks for hundreds of millions of years, preserving paleo-weathering profiles, saprolites, laterites, and paleosols that give rare glimpses into ancient surface conditions. The shields are not entirely featureless. Fault zones and shear belts mark the sutures between ancient crustal blocks, recording the stresses of early tectonic collisions. Some of these zones remain weak points in the lithosphere reactivated during later tectonic events to localize deformation or magmatism. In a quiet irony, the scars of ancient assembly are often the first places to show signs of change when new tectonic forces act on the continent. Large igneous intrusions cut through shield rocks, remnants of mantle plumes or rifting events that penetrated even these stable interiors. Though younger than the surrounding rocks, these intrusions can themselves be hundreds of millions of years old, their preservation testimony to the long-term stability of the shields. Geophysical surveys reveal that the keels beneath the shields are depleted in basalt-forming elements like calcium iron and aluminum, a sign that large volumes of melt were extracted during their formation. This depletion reduces their density, increasing buoyancy, and further insulating the crust above from subduction and mantle convection. This physical and chemical distinctiveness is one of the main reasons cratonic cores have persisted, while younger, thinner crust has been recycled. The mineral deposits of the shields are another quiet legacy of their long history. Gold, diamonds, nickel, and other minerals occur in economic concentrations formed by processes as varied as hydrothermal circulation, magmatic segregation, and deep mantle transport. In this early Earth, these resources lie untouched, locked in place by the same stability that has preserved the crust for eons. In later ages, their presence will guide human settlement and industry, but here they are simply part of the planet's geochemical architecture. The shields also interact with the atmosphere and hydrosphere in subtle ways. Their high elevation relative to surrounding basins can influence drainage patterns, directing rivers toward continental margins or into interior basins. Their chemical stability means they release fewer soluble ions into rivers compared to younger volcanic terrains, subtly affecting ocean chemistry over long timescales. The quiet observation is that even the most ancient and stable parts of the crust remain active participants in Earth's surface system, shaping water flow, sediment composition, and biogeochemical cycles. As the continents evolve, the shields serve as anchors around which younger crust accretes. Fragments of island arcs, oceanic plateaus, and smaller continental blocks are sutured to their margins during orogenies, adding new material while leaving the core largely intact. This process continues through the cycles of supercontinent assembly and breakup, each time enlarging the continental mass but preserving the ancient nucleus. The persistence of the shields across billions of years is a reminder that geological stability is not the absence of change but the outcome of countless changes that leave a structure more resistant to destruction than to survival. Beneath their quiet surfaces lies a record of the planet's earliest tectonic, magmatic, and sedimentary processes, a record that, though incomplete, is the most durable archive of Earth's formative ages. The continents are not fixed forms, but shifting mosaics assembled through the repeated joining and sundering of landmasses in cycles that span hundreds of millions of years. Over deep time, fragments carried by drifting plates converge to form supercontinents, vast aggregations of nearly all the planet's continental crust. These assemblies alter every aspect of the Earth system. Mantle convection patterns reorganize beneath the weight of the supercontinent climate shifts, as ocean circulation changes and the arrangement of mountains, basins, and volcanic arcs is rewritten. The irony is that while a supercontinent might endure for 100 million years in geological terms, it is only a temporary arrangement destined to fragment and disperse. The earliest examples of such large-scale assemblies are difficult to reconstruct, for the rock record becomes sparse and fragmentary with age, yet evidence suggests that by the late Archean and early Proterozoic continents were already clustering into larger configurations. Paleomagnetic data from ancient rocks preserve the orientation of the magnetic field at the time they formed, allowing geologists to infer past positions of crustal blocks, though these reconstructions grow uncertain beyond 2 billion years ago. Another quiet observation is that the continents, though seemingly anchored in place, have each travelled tens of thousands of kilometres over their histories, crossing latitudes and rotating, relative to one another in the slow choreography of plate motion. Supercontinent assembly typically occurs through a series of orogenies mountain-building events, where collisions between continental blocks crumple and thicken the crust. At these collision zones, deep-rooted faults and sutures mark the boundaries between once separate terrains. Granitic intrusions and high-grade metamorphic belts record the immense heat and pressure of these events, while fold and thrust belts preserve the compression of shallower crustal levels. The sediments caught in these belts, once deposited in passive margins or inland seas, are uplifted and deform their fossils when life is more abundant or mineral layers becoming markers of ancient geography. The irony here is that the mountains raised in these collisions begin eroding almost as soon as they form feeding sediments into new basins along the supercontinent's flanks. The interiors of supercontinents often become tectonically stable for long periods, developing vast cratonic plateaus and broad sedimentary basins that accumulate thick sequences of relatively undisturbed strata. These basins can preserve records of climate weathering and atmospheric composition over tens of millions of years. In arid interiors, evaporate deposits form in shallow lakes and seas, while in wetter climates, fluvial and deltic systems spread sands and muds across wide plains. These deposits, later buried, become part of the geological memory carried forward into the next cycle of breakup and assembly. A softer observation is that the calm interior regions of a supercontinent far from the active margins are often where the quietest and most continuous records are kept, even as the edges experience constant upheaval. Breakup begins when heat accumulates beneath the supercontinent, weakening the lithosphere and creating rifts. Mantle plumes rising from below can accelerate this process, thinning the crust and producing vast volcanic provinces that blanket the land in basalt. As rifting progresses, linear seas form and expand into new ocean basins, dividing the supercontinent into smaller continents that drift apart on diverging plates. These young margins often become sites of prolific sedimentation, as erosion of rift shoulders and volcanic highlands fills the adjacent basins. The quiet paradox is that the forces tearing a supercontinent apart also create new passive margins that will over time gather sediments and perhaps serve as the foundations for future collisions. Each supercontinent cycle leaves behind a distinct imprint on the crust. Ancient mountain belts become sutures that guide future tectonics. Cratonic keels thickened during collisions resist subduction in later cycles. Sedimentary basins filled during stable intervals provide resources and records for future geologists to study. Isotopic systems such as neodymium and hafnium track the age and origin of continental crust, revealing pulses of growth associated with supercontinent assembly and breakup. These geochemical signatures, preserved in detrital minerals transported far from their source, allow the reconstruction of supercontinent histories even when direct structural evidence is gone. The persistence of these cycles suggests a balance in Earth's dynamics. Continents are too buoyant to be subducted wholesale, so they accumulate, rearrange and recycle material in ways that maintain their overall volume while constantly altering their arrangement. Another quiet irony is that while the continents change their positions and shapes endlessly, their total area has remained roughly stable for billions of years. The impact of supercontinent cycles extends beyond geology. Large land masses influence atmospheric circulation, ocean currents, and the distribution of rainfall, affecting erosion rates and sediment delivery to the oceans. When continents cluster at high latitudes, ice sheets can develop, drawing down sea level and altering global albedo. When they lie near the equator, weathering rates and carbon dioxide drawdown may increase, influencing long-term climate stability. The interaction between continental position climate and erosion feeds back into the growth and modification of the crust itself, closing the loop between surface processes and deep Earth dynamics. The assembly and breakup of supercontinents also affect the distribution of mineral resources. Collision zones concentrate metals in mountain belts through magmatic and hydrothermal processes, while rift zones associated with breakup can host evaporates, hydrocarbons, and other resources tied to sedimentary environments. These deposits are geological legacies of the supercontinent cycle, preserved in the crust long after the landmasses themselves have moved on. Even in this early stage of Earth's history, before life becomes a major agent of change, the supercontinent cycle is shaping the crust in ways that will define the planet's long-term evolution. The continents are learning through repeated assembly and dispersal how to endure, building stable cores, creating complex margins, and storing their history in rocks that will outlast the oceans around them. In each cycle, the balance between stability and change is struck anew, and the crust emerges with a slightly different composition, structure, and arrangement. Over billions of years, this process will weave together the record of Earth's surface, a story told not in a single unbroken narrative, but in chapters separated by the slow turning of the tectonic page. Iron begins to leave its invisible solution in the world's oceans and settle into layers on the seafloor, a transformation recorded in the broad bands of hematite and magnetite that will one day be known as banded iron formations. These deposits, alternating between iron-rich and silica-rich layers, accumulate over millions of years, the product of chemical reactions between dissolved iron and oxygen, produced either by early microbial activity or abiotic photochemical processes. The oceans before this shift are rich in dissolved ferrous iron, kept soluble by the lack of free oxygen in the atmosphere. With the appearance of even trace oxygen in certain regions, the iron oxidizes to ferric iron, which precipitates and settles to the bottom in fine particulates. The irony is that these massive geological structures, visible from space when exposed in the modern era, began as reactions invisible to the eye, occurring quietly in the depths. In places where volcanic activity or hydrothermal vents feed iron into the oceans, the precipitation can be especially intense, creating thick sequences of layered ore. Some of these deposits are interbedded with volcanic flows or pyroclastic material, preserving a record of both submarine volcanism and ocean chemistry. Others are deposited in quieter shelf environments, building layer upon layer with little interruption. A softer observation is that the iron, once part of the deep crust or mantle, has travelled an immense cycle, liberated by weathering and hydrothermal alteration, carried invisibly in water, then locked into the crust again as solid mineral layers. The formation of banded iron formations is not continuous through all time. It is concentrated in certain intervals when ocean chemistry and oxygen production align. These intervals are tied to broader planetary changes in atmosphere and biosphere, though in this early era the precise triggers remain debated. Some scientists suggest that localized oxygen, oases in shallow seas, allowed iron precipitation long before oxygen accumulated globally in the atmosphere. The mystery of these deposits is that they require both oxygen to oxidize the iron and an anoxic environment to keep the iron dissolved until precipitation, two conditions that must exist in close proximity. This paradox is resolved in part by the stratification of early oceans, where shallow waters in contact with the atmosphere could be oxygenated, while deeper waters remained reducing. Periodic mixing events, perhaps driven by climate or tectonics, would then allow the two layers to interact, triggering precipitation. Banded iron formations not only remove iron from seawater, but also sequester oxygen indirectly, as the oxidation of iron consumes it. This means that the buildup of oxygen in the atmosphere may have been delayed in part by the vast capacity of the oceans to absorb oxygen through iron oxidation. The result is a drawn-out interplay between geological and atmospheric processes, with the continents playing a central role by supplying iron through erosion and hydrothermal systems. Volcanic arcs, mid-ocean ridges, and submarine hotspots all contribute to the input of iron into seawater. On the continents, chemical weathering of mafic rocks releases additional iron carried by rivers to the sea. In both cases, tectonic activity determines the supply rate, linking the production of these deposits directly to the rhythms of plate motion and crustal growth. Over time, the accumulation of banded iron formations locks away vast quantities of iron in the crust, creating later economic deposits that will be mined extensively. The quiet irony is that these future resources are being laid down now, in environments devoid of the life forms that will one day exploit them. Their preservation depends on later tectonic stability. In some regions they will be folded, metamorphosed and buried during orogenies, yet still retain their characteristic layering. In others, they will be uplifted and eroded, their iron released once again to rivers and oceans. These deposits are also an archive of Earth's geochemical past. The ratios of certain isotopes such as iron and rare earth elements in banded iron formations provide clues to the temperature, chemistry and biological activity of ancient oceans. The silica layers, often composed of chert, may form from the precipitation of dissolved silica or from the accumulation of microcrystalline quartz replacing earlier minerals. Even in the absence of abundant life, these layers can incorporate microscopic textures and mineral phases that hint at the presence of microbial mats or other surface-bound communities. In the broader context of continental evolution, banded iron formations reflect a stage where weathering and sedimentary processes are deeply integrated into the crust's growth. The delivery of dissolved iron to the oceans requires continental surfaces exposed to erosion rivers to transport materials and tectonic systems to supply fresh volcanic rock. Once deposited, these iron-rich sediments become part of the sedimentary rock cycle, subject to burial metamorphism and incorporation into the continental crust. In some orogenic belts, banded iron formations become deformed and recrystallize, their layers contorted into complex folds, yet still traceable as distinct chemical units. The global distribution of these deposits shifts over time following the assembly and breakup of continents. When continents cluster near the equator, weathering rates in warm, wet climates can accelerate iron delivery to the oceans. When they drift to higher latitudes, glacial erosion can expose fresh rock and deliver pulses of sediment to the seas. This climate tectonic coupling influences not only the volume of iron deposited, but also the style and location of deposition. Another quiet observation is that while the formation of banded iron formations declines sharply, after the Proterozoic, the processes that create them, weathering, transport, precipitation, never truly stop. They simply shift into new geochemical contexts as the planet's oxygen levels and ocean chemistry change. In the deep future, remnants of these deposits will serve as markers in the geological record, their distinctive layering and mineralogy instantly recognizable as belonging to a specific window in Earth's history. For now, they are one more layer in the growing archive of the continents, a chemical signature tied to both the solid Earth and the evolving oceans. Each band, alternating light and dark, is a record of conditions that cycled over timescales far beyond the perception of any living thing in this era. Together they form sequences hundreds of meters, thick testaments to the slow interaction of tectonics, weathering, chemistry, and perhaps the earliest stirrings of biology. Like the continents themselves, these iron-rich stones are born of movement and change, yet they lie in stillness for eons, carrying in their layers the memory of a world learning how to breathe. The continents, though growing more stable with each cycle of assembly and renewal, remain active participants in the slow shaping of the planet's surface. Mountains rise where plates collide, but these highlands are temporary features destined to be leveled by erosion and carried away grain by grain to lowlands and seas. Valleys deepen as rivers carve their paths, meandering across floodplains and delivering sediments to deltas that shift position with each flood season. Over tens of millions of years, the products of erosion build vast sedimentary wedges along continental margins, thick accumulations that can be preserved for future ages or dragged into subduction zones to feed new volcanic arcs. The irony is that in dismantling the land, erosion creates the raw material for its preservation, as sediments once rock become rock again in another form. In the interiors of the continents, weathering profiles deepen, especially in regions where tectonic stability allows soils to remain undisturbed for millions of years. Chemical weathering strips soluble elements from rock, concentrating quartz, and forming clay-rich layers that alter drainage and nutrient cycles. In wetter climates, lateritic soils rich in iron and aluminum develop, while in cooler, drier regions, thin soils and fractured bedrock dominate. These differences in weathering and soil development influence the color and chemistry of sediments that eventually reach the sea, subtly recording the climate of their source regions in mineral proportions and isotopic signatures. Another quiet observation is that while the continents appear inert from space, their surfaces are in constant transformation under the combined effects of climate hydrology and time. Tectonic forces continue to redistribute the continents, carrying them across latitudes and into new climatic regimes. A block that once lay near the equator, subject to intense tropical weathering, may drift into polar latitudes and be sculpted by ice sheets in a later era. These glaciations, when they occur, are powerful agents of erosion, grinding rock to fine silt that is carried far by wind and meltwater. The debris left behind moraines outwash plains and drop stones becomes part of the sedimentary record, preserving a snapshot of the Earth's climate and continental arrangement at that moment. Even in times without global ice mountain, glaciers can form at high elevations, carving cirques and U-shaped valleys that persist long after the ice has melted. Along continental margins, the interplay of tectonics and sea level controls the shape of coastlines. In some regions, passive margins with broad shells host thick accumulations of sediment that may one day be uplifted into coastal plains or eroded into cliffs. In others, active margins with narrow shelves and steep slopes focus sediment into deep-sea fans fed by submarine canyons. Turbidity currents triggered by earthquakes or slope failures carry material to the abyssal plain, where it accumulates in layers that may be preserved for hundreds of millions of years before being scraped off and added to another continent. These submarine fans, when uplifted, form some of the most extensive sandstone deposits in the geological record. In the long term, continental interiors are shaped by the balance between uplift and erosion. Mantle dynamics can produce gentle doming of the crust far from plate boundaries, raising regions and accelerating erosion without direct tectonic collisions. Conversely, sediment loading in large basins can cause subsidence, deepening the basins and allowing even thicker sedimentary successions to accumulate. These vertical motions, though subtle on human scales, create shifting patterns of river drainage, sediment delivery and erosion that feed back into the growth and modification of the crust. Volcanism also continues to play a role in shaping continental surfaces even in regions far from active plate boundaries. Intraplate volcanism, often driven by mantle plumes, can produce volcanic plateaus, isolated cones and lava fields that alter drainage patterns and add new material to the crust. Over time, these volcanic rocks weather into fertile soils, further influencing the landscapes they occupy. Yet these additions are often transient. Erosion quickly reduces volcanic edifices to low hills, their lavas broken down and incorporated into sedimentary systems. A gentle analogy is that of a loom endlessly reweaving its cloth tectonics, and volcanism add threads from below, while erosion and sedimentation rework them from above, creating a continuous but ever-changing fabric. The continents also act as regulators in the global carbon cycle. Chemical weathering of silicate rocks consumes carbon dioxide, transporting it to the oceans, where it is stored in carbonate sediments. This process is temperature and precipitation dependent, meaning that the movement of continents into different climatic zones can influence atmospheric composition over millions of years. In the deep past, this feedback has likely helped stabilize Earth's climate, preventing runaway greenhouse or icehouse conditions. Another quiet irony is that the continents, in wearing themselves down, may have contributed to their own habitability. As erosion exposes fresh rock, it also exposes minerals that release nutrients into rivers and soils. In later eras, these nutrients will support ecosystems that in turn accelerate weathering and sedimentation. Even before life plays a significant role, the continent's interaction with atmosphere and water sets the stage for future biological cycles. In places where tectonic uplift is slow and erosion minimal, ancient land surfaces can be preserved for extraordinary lengths of time. These paleosurfaces, marked by deep weathering profiles or planation surfaces, can remain stable for hundreds of millions of years, interrupted only by burial beneath younger sediments or volcanic flows. When later exposed, they reveal the stability and persistence possible in certain continental interiors, offering rare direct windows into ancient landscapes. The continued drift of the continents ensures that no surface remains untouched forever. Margins that are now passive will one day become active, uplifted into mountains or consumed by subduction. Interiors that are now stable may fracture in future rifts, birthing new ocean basins. Every shift redistributes the balance between erosion and deposition, destruction and creation. The quiet observation is that the continent's permanence is an illusion born of human timescales. In the rhythm of deep time, they are as changeable as the seas, and yet through this constant reshaping, the continents have maintained a core identity, stable cratons surrounded by more active belts that allows them to persist while their forms evolve. Each grain of sand on a beach, each boulder in a mountain stream, each layer in a distant sandstone cliff is a product of this cycle, linking the highest peaks to the deepest basins in a continuum of movement. The continents endure not by resisting change, but by embracing it, their growth and survival dependent on the very processes that wear them down. The continents, now layered with the products of billions of years of tectonics, magmatism, sedimentation and erosion, continue to evolve through the interplay of processes that have been in motion since their first fragments appeared. Their shapes shift as plates converge, diverge and slide past one another, yet the core structure, a buoyant lithosphere riding high above the mantle, remains. At active margins, mountains rise as oceanic plates sink beneath continental crust, the resulting magmatism and deformation adding new material to the edges of the land. In contrast, passive margins, where continents drift away from spreading centres, accumulate thick piles of sediments eroded from their interiors, creating broad shelves that may one day be uplifted into coastal plains or thrust into mountain belts. The irony is that the very features marking the continent's stability today often hold the seeds of future upheaval, awaiting only the next cycle of collision or rifting. Within the continental interiors, stable cratons anchor the landmasses. Their deep keels, chemically depleted and mechanically strong, insulate them from the mantle's convective currents and protect their ancient rocks from destruction. Around these cores, younger orogenic belts and sedimentary basins tell of past collisions, rifts and volcanic arcs now sutured to the continental mass. These belts preserve metamorphic rocks formed at great depth, volcanic sequences from long-vanished arcs and sediments deposited in basins that no longer exist. A softer observation is that the continents are mosaics of countless fragments, each carrying its own history bound together into a single evolving whole. The ongoing growth of continents occurs in pulses. Large-scale magmatic events such as those associated with mantle plumes can rapidly add new crustal material in the form of volcanic plateaus or granitic intrusions. Accretion of island arcs, microcontinents and oceanic plateaus at subduction zones steadily enlarges the continental footprint. Sediments from erosion of highlands are buried lithified and in some cases metamorphosed into new continental rock. This recycling of material, whether through magmatism or sedimentary processes, ensures that the chemical diversity of the crust increases with time. Another quiet irony is that continents grow not only by addition, but also by transformation, turning old rock into new without adding significant volume. Climate remains intertwined with continental evolution. The position of land masses influences atmospheric circulation and precipitation patterns, which in turn control rates of erosion and chemical weathering. In warm, wet climates, silicate weathering draws down atmospheric carbon dioxide, influencing global temperatures. In cold, dry climates, weathering slows, allowing carbon dioxide to accumulate from volcanic outgassing. These feedbacks help regulate Earth's climate over geologic time, making the continents not just passive recipients of climate's effects, but active participants in its control. In later ages, the spread of vegetation will further amplify this feedback, but even now, the interplay of rock, water, and atmosphere shapes the conditions under which the continents evolve. The topography of the continents changes continually. Mountains erode, basins fill, river systems adjust their courses in response to tectonic and climatic shifts. Isostatic adjustment raises areas where ice sheets or sediments have been removed and lowers those loaded with new deposits. Volcanism occasionally reshapes the land, whether in the form of flood basalts that cover thousands of square kilometers, or smaller-scale eruptions that alter drainage and relief. Each change leaves traces in the stratigraphic record unconformities, where erosion has removed earlier layers, volcanic ash beds marking brief but widespread events, sedimentary sequences that record long-term environmental trends. The continents also act as long-term reservoirs for elements extracted from the mantle. Over time, incompatible elements become concentrated in the continental crust, altering its composition and ensuring that it differs fundamentally from the oceanic crust, being continually created and destroyed at spreading centers. This compositional difference is why continents are buoyant and why they tend to survive while oceanic crust does not. It is also why the continents are geochemically heterogeneous, with regions enriched in certain elements or minerals depending on their unique histories of magmatism, metamorphism, and sedimentation. Another quiet observation is that this heterogeneity built up through billions of years provides the geological complexity upon which future biological and human systems will depend. Supercontinent cycles continue each assembly and breakup, redistributing continents across the globe. When continents cluster, mountain ranges rise along their sutures, vast plateaus develop, and the interiors experience long intervals of stability. When they break apart, rifts and passive margins create new pathways for sedimentation and magmatism. These cycles not only rearrange geography, but also influence mantle convection, climate, and ocean circulation. Over time, the continents drift through different latitudes, experience different climates, and undergo repeated transformations of their surfaces and margins. In this way, the history of the continents is inseparable from the history of the planet's interior and exterior systems. The sedimentary record within the continents becomes thicker and more complex with each cycle. Basins accumulate sequences of rock that, if preserved, can span hundreds of millions of years, recording changes in sea level, sediment sources, and climate. In some places, these sequences are later buried and metamorphosed, erasing their original structures while preserving chemical evidence of their origin. In others, they remain intact until uplift exposes them where wind and water resume the slow work of erosion. The durability of certain minerals, zircon most famously, allows geologists in the distant future to reconstruct these cycles even when much of the original rock has been lost. The continent's evolution is not a march toward permanence, but a balancing act between processes that create and processes that destroy. Magmatism, accretion, and sedimentation add new material. Erosion, subduction, and metamorphism transform or remove it. The net result over billions of years has been a gradual increase in the volume of continental crust, but the pace is uneven, marked by periods of rapid growth and long intervals of recycling. This unevenness is a reflection of the dynamic nature of the Earth system, where internal and external processes are constantly interacting. A gentle analogy is that of a shoreline constantly redrawn by tide storms and currents, yet maintaining a recognizable presence through time. The continents, for all their change, remain the enduring face of the planet. By this stage in their history, they are robust enough to withstand most tectonic and erosional forces without disappearing entirely. Their interiors are anchored by cratons that have survived since the Archean. Their margins are sites of ongoing renewal and reworking. Each part of the continent, whether ancient shield or young orogenic belt, plays a role in the long-term stability of the whole. In the rhythm of deep time, there is no final state, only the continued interplay of forces that keep the continents alive as geological entities. They rise, break drift, and reform their surfaces, shifting, yet their essence preserved in the buoyant crust that has learned to endure. Every grain of quartz in a sandstone, every folded mountain belt, every granite pluton is part of this immense ongoing cycle, a record of a planet in motion, and of land that has grown through the very processes that wear it down. Now the continents rest beneath the sky, their outlines softened by distance, their motions hidden within the slow mathematics of the mantle. Mountain chains stand as low shadows, their highest peaks weathering grain by grain into the rivers that meander toward the sea. Broad plateaus breathe heat into the thin air above them, while valleys hold still pools of water, reflecting clouds that drift without hurry. On the coasts, waves press and retreat in the same patient rhythm they have followed for eons, wearing cliffs into beaches, carrying fragments of stone into the deep. In the interiors, the cratons lie quiet, their roots sunk deep into the mantle, their surfaces brushed only by wind and rain. Every rock here carries the memory of change, of collisions and rifts, of fire and flood, but none of that history is urgent now. The land simply is anchored in the present moment. The atmosphere moves softly across its edges, carrying fine dust from deserts, salt from oceans, moisture from forests, each grain and droplet finding its place. In the deep basins, sediments settle through still water, joining layers that have been forming since before the continents were whole. Far below the mantle continues its slow currents, but the crust above feels only a steady, distant warmth. The cycle of growth and loss continues, but tonight it is beyond sight or sound. The continents sleep in their shapes, knowing they will rise again in other forms under other skies, yet content in the stillness between. No single mountain will remain forever. No coastline will hold its curve for all of time, yet the idea of land endures, resting now under a thin and quiet sky, waiting for the next turn of the planet's long and patient hand.